Welcome to this explainer. Today we're kicking off part 1 of our deep dive into system-neutral earthing methods. We're specifically focusing on exactly how extra high voltage and high voltage networks get grounded across the top tiers of the voltage ladder.
Now, let's just get straight into it, because getting your earthing strategy wrong, that is definitely not some minor administrative compliance issue or a paperwork error. We're talking about the defining physical factor that decides if a massive electrical fault clears safely or if it literally destroys a substation and turns into a deadly hazard. It is absolutely the primary lever we have for controlling fault current. So here is the overarching rule you've got to memorize for the grid. The system is split into 4 voltage tiers, and every single one of those tiers tackles the physics of grounding in a completely different way. 4 tiers, 4 totally distinct earthing philosophies. You absolutely cannot just guess or try to force a one-size-fits-all approach here.
First up, extra high voltage, or EHT, solid ground.
The engineering documentation is incredibly explicit on this. Both the 400 kilovolt and the 230 kilovolt sides of EHT transformers are solidly grounded, period. There is absolutely zero resistance deliberately inserted between the neutral point and the earth. To really grasp why we do this, just think of a massive dam holding back water. Solid earthing? It's like opening the floodgates completely for totally unrestricted flow. On the flip side, resistor earthing acts more like a partially closed current-limiting valve. But up here at the very top of the grid, we want those floodgates wide open. And here is exactly why EHT goes with solid earthing. Solid earthing yields the absolute highest earth fault current. By letting that massive current flow completely freely, it guarantees that the protection relays are going to detect that unmistakable surge and trip instantly. We're talking clearing the fault in literal milliseconds. Moving on to Tier 2, high voltage at 66 kilovolts, the current-limiting valve. Okay, so here's the catch. We can't just leave those floodgates wide open at 66 kilovolts. It doesn't work. To deliberately cap that fault current, the 66 kilovolt system is grounded through a very specific piece of equipment. We use a 19.5 ohm neutral earthing resistor, or NER. This whole resistor philosophy is all about balancing 2 intensely competing needs. First off, it acts as that valve we talked about. It deliberately caps the fault current magnitude, which is absolutely crucial for protecting equipment from destructive forces and, reducing those dangerous step and touch potentials for anyone nearby. But at the exact same time, it keeps the current just high enough to reliably trigger the protection relays. It's really just this perfectly calculated mathematical balance. All right, let's lock this spec into your memory right now with a quick check. Based on what we just went through, what is the exact neutral earthing resistor value required at the 66 kilovolt tier? Burn this exact value into your mind, 19.5 ohms. This is the critical engineering specification you've got to know for 66 kilovolt earthing. If you see 19.5 ohms out there, you know exactly which tier of the grid you're dealing with. Okay, so we have successfully mapped the top half of the voltage ladder. Before this explainer, you already knew busbar architecture, and now you've got extra high voltage and 66 kilovolt earthing methods down. But hey, our 4-tier table is only half built. We still need to solve for the 22 kilovolt medial voltage distribution networks, plus the low voltage tier right below that. I'm going to leave you with a bit of a provocative physics question to chew on. If the 66 kilovolt system requires a 19.5 ohm valve, does a lower voltage tier need more resistance or less resistance to keep the system and the public safe? Really think through the logic of that carefully, because honestly, the answer completely defies what most people guess. Join us in part 2 of this explainer, where we're going to uncover the surprising grounding rules for medium and low voltage systems, and we'll also dive into the crucial material rule. Catch you then!